Great. Firstly, thanks to the organizers for inviting me. So yeah, I'm going to talk about Floer theory and Cobordisms between exact Lagrangians, and everything original that I talk about will be joint work with Ivan Smith. So firstly, I'll talk about some background and some of the questions that we'll ask. And then I'll talk about frame bordism, which is the main sort of invariant that we'll use to distinguish certain Lagrangians. And then only after that, I'll actually state theorems, because they'll be in terms of frame cobordism. And then finally, depending on how much time there is, I'll talk some amount about Floer theory and the versions of Floer theory that we use. So we'll start with some background plus questions that we care about. So for all of today, we're going to have some symplectic manifold X of dimension 2n. And we're always going to, for today, we're always going to assume it's Liouville. So this is a non-compact symplectic manifold where the symplectic form is exact. It's d lambda for some one form lambda, and it behaves nicely at infinity. That's not a precise statement. It just means there's outside of compact subsets, you have some nice behavior. So the main examples we care about, I guess, are if X is the cotangent bundle of a closed manifold. This is one of the principal examples that's of interest. Or if X is a plumbing of closed manifolds. Sorry, of cotangent bundles of closed manifolds. Maybe we can have three plumbings. Or any smooth, complex affine variety. Okay, so if I pick one of these symplectic manifolds, the question is then, what are the Lagrangians in it? Roughly, at least, the more precise question that we'll talk more about today is what are the diffeomorphism classes of closed exact Lagrangians? So we have some strong conditions. L inside X. So just to recall, this is a half-dimensional submanifold, so it's dimension n. And this one form I mentioned before, restricted to L, this is some one form on L is exact, instead of just being closed like an ordinary Lagrangian. So what kind of things might we hope for in this question? Well, one of the conjectures in this direction is the nearby Lagrangian conjecture, which really says something a little bit stronger, but in particular implies that if X is a cotangent bundle, then any such L is diffeomorphic to Q. So any closed exact Lagrangian in a cotangent bundle is diffeomorphic to Q. So that's what we'd hope. So we're not going to prove that today, but that's sort of the type of question that we're interested in, and various generalizations of this you could ask for restrictions there. So in that direction, what is known due to Abouzaid and Kragh, later reproved by Guillermo, is that, again, if X is a cotangent bundle, then any closed exact Lagrangian L inside X is homotopy equivalent to Q. So, you know, same homology, same homotopy groups, etc. So if you wanted to disprove this conjecture, the first invariant you try to use would be homology and homotopy groups and pi1 and stuff like that, and they don't work, is what this tells you. So now you can ask sort of how different can homotopy equivalent manifolds be? And this is obviously a pretty hard question, but if you start with maybe the simplest version of this, which is like what types of manifolds can be homotopy equivalent to a sphere, you find the following, which is due to Caveira-Milner. and this is still pretty hard to prove already, is that there are exactly 28 distinct diffeomorphism classes of manifold, which are all homotopically equivalent to S7. So there's exactly 28 manifolds which are all non-diffeomorphic to each other, but all homotopically equivalent to S7. Sorry, I mean oriented. And similarly, there are exactly 2 diffeomorphism classes of oriented manifolds which are homotopically equivalent to S8. So you can ask, can we rule these out, these specific manifolds, from embedding into a cotangent bundle of S7 or S8? And the answer is going to be no for S7 and yes for S8. And sort of in the next section, I'll try to explain what the difference between 7 and 8 is and what invariant we'll use. But I will remark that all 28 of these in dimension 7 and same in dimension 8, all of these are homeomorphic to each other. Surprisingly. Any questions before we move on? Okay, then I'll talk about frame bordism, which is the invariant that we'll use to distinguish these. So firstly, we need some definitions. A stable framing on a manifold M, let's say of dimension n, is an isomorphism of vector bundles Tm plus r to the k with r to the n plus k. And here I mean r to the k as in the trivial rank k vector bundle over M. So I'll write it like this. So this is a little bit weaker than being parallelizable. And a stable framing is a choice of such things. So a stably framed manifold is a pair MC, where C is a stable framing. On M. Okay. So these might not exist. So given M, there might not be any. Or they might exist but be non-unique. But this is all okay for us today. So let's see some examples. First example is a bit silly. The empty manifold is always a frame manifold. Slightly more interestingly, if I take Sn and I embed it inside Rn plus 1 in the usual way, so as the boundary of the disk, then the normal bundle of this embedding is R. It's the trivial line bundle. So this gives us an isomorphism between the tangent bundle and the normal bundle, which is R to the 1, with R to the n plus 1. So this gives us some choice of stable framing. And I'd call this the standard one on a sphere, if pressed. Another example you can take is S1 or S3 with the Lie group framing. So this comes from it being a Lie group, and this will actually be TS1 is isomorphic to R to the 1, or TS3 isomorphic to R to the 3. But these are this framing and this framing on R1 and on S1 and S3 are actually not the same. They're different. And maybe in terms of non-existence, if M has a stable framing, lots of its characteristic classes vanish. So all Pontryagin classes and Stiefel-Whitney classes of M are 0. So in particular, RP2 and CP2 don't have stable framings. So these, yeah, most manifolds don't in general. But, okay, so these are stably framed manifolds, and there's still a lot of these, but we have an equivalence relation on them. So a framed bordism, let's call it W sigma, from M C to M prime C prime. These are stably framed manifolds of dimension n. It's a cobordism W from M to M prime, along with a stable framing on W, which restricts to C and C prime. And I need a minus in here as well. So the stable framing on W restricts to C on M and minus C prime on M prime. And framed bordism is an equivalence relation. On framed manifolds. So now we can consider the quotient by this equivalence relation. And so I'll define the framed bordism groups. To be this quotient. I'll write it as omega framed n. It's defined to be the set of stably framed n manifolds modulo framed bordism. Oh, I should say all my manifolds here are compact without boundary, and my bordisms are also compact but with boundary. So this ends up being an abelian group under disjoint union, and the unit is the empty manifold, because if you disjoint union with the empty manifold, you don't change anything. And in fact, this is a graded ring, or it's this thing is the degree n part of a graded ring. And the product is multiplying manifolds together. And you need to check that if I have two framed manifolds, then the product manifold has framing. Okay, so what do these groups look like? Well, there's infinitely many framed manifolds in each dimension. There's just too many manifolds, but it turns out that this group is actually finite in non-zero degrees. So here's some computations that people have done. In dimension 0, this isn't so interesting. You just get a copy of Z, where these are, framed manifolds in dimension 0 are a finite collection of points with orientations on them. In dimension 1, we get Z mod 2. And the non-zero element in this, the generator, is actually S1 with the Lie group framing. So not only is the Lie group framing on S1 different, it's actually not even frame coordinate to the to S1 with the standard framing. And if we get to dimension 7, we get a copy of Z mod 240. Dimension 8, we get Z mod 2 plus Z mod 2. And what's special about dimension 7 is that all 240 of these elements are of the form S7 with some framing. Or rather, all 240 of these equivalence classes have a representative, which is S7 with some framing. So that's quite surprising, I think. Now, what's different about S8, or dimension 8, is firstly, any exotic sphere, these are these fake spheres which are homotopic equivalent to Sn but not diffeomorphic to it, does admit a stable framing. Again, this might not be unique, but that's fine. And now let's let sigma be the unique exotic S8. Then sort of what's different in dimension 8 to dimension 7 is that it turns out that the frame bordism class of sigma is never equal to the frame bordism class of S8 for any choice of framing on these two things. So with the way I've written this here, you need an extra choice, which is the choice of stable framing. And this is actually strictly non-unique in this case, but it doesn't matter what you choose. But because of this fact here, that all frame bordism classes in dimension 7 are represented by the standard sphere, this isn't true in dimension 7. So this is the fact that we'll use to distinguish nearby Lagrangians in dimension 8 rather than dimension 7. Okay, so I can now state some theorems that are more symplectic again, because that was all topology. And I'll state a sort of more general theorem, and then we'll have some more concrete corollaries. So let's again let X be some Liouville domain, so the symplectic form is exact. And let's let L and K inside X be two different closed exact Lagrangians. So the theorem is we're going to have to assume a lot of things. Yeah, and this is still in progress. So we'll assume a bunch of stuff, and then we'll get some restriction on the difference between L and K and frame bordism group. So let's assume that L and K are homology spheres. Okay, so that's already a pretty strong thing, but you can check this in some cases. And let's also assume that L and K are they have the same Floer theory. So this is just another way of saying they're equivalent in the Fourier category. And here I mean Floer theory over the integers. And now I need to make some technical assumption, which I'll call star, and I won't really talk about again, but I'd like to at least state precisely, is that I fix a stable trivialization of Tx as a complex vector bundle, so Tx plus c to the k is isomorphic to c to the n plus k for some k. These are vector bundles over X. And similarly for L and K, we can't talk about their frame bordism classes if they're not framed stably framed. So this means I have TL plus R to the K, so isomorphic to R to the N plus K. But now I can include both sides of this equation, because TL always embeds in Tx, R to the K into C to the K, R to the N plus K to the C to the N plus K, and I pick a homotopy between the two ways of going around this diagram. And I do the same thing for K. So I won't talk about this condition again, but I will at least say when we use it. And we'll see that this can be verified in some cases. So under these assumptions, so the homology sphere assumption, the Floer theory equivalence, and the tangent bundle assumptions, then we conclude that the difference between the frame bordism classes of L and K in the frame bordism group is 2 torsion. So it's quite small. And we actually get a little bit more, which is that the difference between L and K lives in some subgroup of the frame bordism group, which is things in degree 1 times things in degree n minus 1. And this thing was Z mod 2, which means that this whole subgroup is 2 torsion. So that's where the 2 torsion comes from. Okay. Okay, so that's the more general result. And we had these sort of big, scary assumptions, but these can be verified in some situations, so we can get some more concrete corollaries of this. So the first corollary was already known due to different methods by Abouzaid-Alvarez-Gavela Silvan-Courte and Thomas Kragh, which is that if L inside the cotangent bundle of a sphere is a closed exact Lagrangian, then the frame bordism class of L is again in this same subgroup. And in particular, if n equals 8, then L is diffeomorphic to S8. So here we're applying the theorem where we take one of the Lagrangians to be L and the other Lagrangian to be the zero section. And then sort of work of, I think, Abouzaid and others proves that these two Lagrangians are quasi-isomorphic in the chi category. This assumption on tangent bundles is automatic for degree reasons, it turns out. Yeah. So outside of cotangent bundles, though, we can still get some things out of this. So let's let X be the plumbing of two cotangent bundles of spheres, so the A2 plumbing. And L inside X, a closed exact Lagrangian. Okay. So now this is a more complicated symplectic manifold than the previous one, but it's not necessarily that much more complicated. It's still got pretty small homotopy type. So let's assume that the Maslov class of L is 0. This is some characteristic class, and we're going to assume that n is 0, 4, 6, or 7 mod 8. Then the frame bordism class of L again lives in this same subgroup. So in particular, the exotic S8 does not embed into X. Because n is 0 on 8. So here we're using some other results as well. This uses the fact that any such Lagrange is known to be a homology sphere due to work of Ivan Smith and Ahmed Abouzaid. And here we make this dimension assumption because this actually turns out to make the tangent bundle assumption that I made automatic. So it's true in half of dimensions without any extra work for this symplectic manifold, which is nice. Okay, so now I can talk about the way we access these invariants. So we'll use some version of Lagrangian Floer theory, but we'll use sort of a more recent version of it constructed by Tim Large. So I'll sort of explain what he constructs and then what we do with it. So let's take, once again, X, some medieval domain, and L and K inside X, some closed exact Lagrangians. So what we normally do is we pick some almost complex structure J on X, and it needs to be compatible with omega and needs to be sufficiently nice outside of compact subsets, as always. And then we consider sort of some moduli spaces of holomorphic curves. So I'll write M hat XY for sort of the hat means uncompactified so far. This is going to be defined to be the set of maps U from the infinite strip, such that we have the Cauchy-Riemann equation holds, as well as some boundary conditions, which I'll write and I'll draw. So U of R times 0 is inside L. If here is the infinite strip, R times 0, 1. This side gets into L. U of R times 1, then K. U of plus infinity is Y. U of minus infinity is X. And these things always have an R's worth of automorphisms, which I quotient by. So so far, if you pick so I guess you need to pick J generically and maybe some extra data. But if you do this, then this will actually be a manifold of finite dimension, which is nice. And then we compactify this in the usual Gromov compactification to what I'll call MXY, which is M hat union broken strips, which are things that look like, instead of this thing, we have things like this, where I go from X to Y, but I break at some other intersection point Z. And this, sorry, I should have said, where this is where X and Y are intersection points between L and K. So it's been known for a while that these uncompactified moduli spaces are always, or at least generically, smooth. But more recently, Tim Large proved that these compactified moduli spaces are also smooth. So they're compact, smooth manifolds with corners. And we can also describe the boundary strata. So the boundary of MXY is exactly the strips that break at least once. So these are the union over other intersection points Z intersect K, M XZ times M ZY. And each of these can break multiple times, and then you'll get to the higher codimension strata of the boundary, because we don't just have boundary, we actually have corners. So not only does he prove this, but he also proves that if we assume star, so this is this very strong condition about tangent bundles on all of the Lagrangians and X, then all the MXYs are stably framed. And this is compatible with strip breaking. And what do I mean by this is, I mean that it's compatible with this equation here. So if MXY has a stable framing, that restricts to one on the boundary. And if I have stable framings on MXZ and MZY, then their product has a stable framing, and I need this to agree with this equation. So that's some coherence. Okay, so once you have all of this structure on the moduli spaces, what you normally do to build Floer theory over Z is I define a chain complex CF star of LK over Z to be the free chain complex generated by their intersections between L and K. Direct sum over X in intersect K, Z times X. Okay. And then I give this a differential. Oh, I should say that, so I haven't written it, but there is a grading on this, on all of these as well. And the differential D sends X, some intersection point between L and K, to a sum over other intersection points, something times Y, and that something is the count of points in this moduli space MXY. And I'm just going to define this count to be 0 if the moduli space has dimension not 0. And then if it has dimension 0, because it's a compact manifold, it's a finite number of points, and that's the number that I take. And then I define the Floer homology to be the homology of this chain complex. Okay. Now, the thing is that throughout all of this, so far, we've only used the 0-dimension moduli spaces. We have a lot of other moduli spaces around, and we've just thrown them all away. Maybe we've used the one-dimensional ones when you actually prove that this is a differential, but that's still not very many of them. So we'd like to use all of the rest of them. So remember, we wanted to study frame bordism, and all of these MXYs are frame manifolds, so it's sort of high dimensions, possibly. So it makes sense to remember that we had them. So sort of the next thing that Tim Lodge does, following a strategy originally envisaged by Cohen, Jones, and Siegel, is he builds sort of Lagrangian Floer theory over the frame bordism ring. So HF of LK over frame bordism. This is how I write it, which is a spectrum whose homology is the Floer theory we had before, the Floer homology we had before. So for all of the proofs here, we'll need the fact that we had a spectrum, but for the moment, we can treat this like a DG module, or even just a module, I guess, over the frame bordism ring, so some graded ring, such that roughly the Floer theory of L and K over frame bordism ring tensored over frame bordism ring with Z is the usual Floer theory. So we kind of treat this as Floer homology over a different ring, which when we base change, we get back the original Floer homology that we started with. But so in particular, this new invariant determines Floer homology over Z, but the reverse is not true. Floer homology over Z does not determine this Floer homotopic. Okay. And this is built using moduli spaces of all dimensions. So all the positive dimensions is what we need. So we also, with ordinary Floer homology, we actually had a lot more structure than just a bunch of chain complexes. We had lots of, we had a product structure, for example. We even had A-infinity structures. And we don't get the A-infinity structures here. They should exist, but Tim hasn't built them. It becomes a lot harder. But he builds the product in particular. So this is some map from HF of L prime in frame bordism, tensored over frame bordism with Floer homology for L prime and L double prime to HF of L double prime in frame bordism. And he also proves that this is homotopy associative. As with usual Floer homology. So what this amounts to is essentially he's built a spectral Donaldson-Foucault category. So this sort of looks, yeah, so the construction can be quite complicated along the way, but we can at least understand it in some examples. So suppose L intercept K is 2 points, X and Y. So there's only one non-empty moduli space. Which is MXY. And So this thing's compact with boundary and corners, but we knew how to describe the boundary strata, and these had to be things that break at other intersection points. If there aren't any other intersection points, then it turns out that this thing has no boundary. So this is actually MXY is a closed manifold. So it's a closed stably framed manifold. And let's say it's of dimension I. So it determines a class in the frame bordism ring. And what the construction gives you is that HF of LK over frame bordism is it's actually the cone over multiplication by MXY. So here I'm kind of using this analogy to modules over a graded ring. So this is a map from the frame bordism ring to itself, but because this element is in non-zero degree, it's not really from frame bordism ring to itself, I need to shift one of these by I. Okay. Yeah, so this is what this looks like. And it turns out that if the dimension of this moduli space is n-1, then the homology of this thing over Z is going to be isomorphic to the homology of a sphere. So remember that we were, the case we wanted to study was when the homology of these two Lagrangians is the homology of a sphere. And so here we've come up with some example that could reproduce that. And in fact, it turns out if the homology, the Floer homology of L and K over Z is the homology of a sphere, then the reverse is true. Then the Floer homology of L and K over the frame bordism ring also has to be equivalent to the cone over multiplication by some class. Let's call it theta. Where theta is some object, some element of the n-1 dimensional frame bordism ring. But if we've assumed this more generally, then theta is represented by some frame manifold, but you end up building it algebraically, and so it's not so clear how to get it from moduli spaces. Whereas before we had sort of a description of it in terms of one moduli space. So what we've built so far is we've built some invariant that seems to use more of the frame manifolds that we had floating around, but we'd like to link it back to the frame manifolds that we started with, which were L and K. So the main technical lemma that we'll use is the following thing, is if L and K, so once again, they're closed exact Lagrangians in the Liouville domain, but if they satisfy star, which is, remember, was this strong orientation or strong tangent bundle hypothesis, and if L and K have the same Floer theory over the frame bordism ring, so said differently, this means they're isomorphic in this spectral Donaldson-Foucault category, then they actually have the same frame bordism class. And you actually get this in the frame bordism groups of X, but I didn't define what that was. So this tells us that these new invariants that I just spent a few minutes talking about do actually help us with the question that we were originally interested in. So the problem is that we've assumed that in this lemma, we want to assume that L and K have the same Floer theory over the frame bordism ring, and that's a really strong assumption, and we don't know how to verify this in practice is the problem. But this does beg the question, is if L and K have the same Floer theory over Z, then do they also have the same Floer theory over the frame bordism ring, because the theorem that we wanted was that if L and K had the same Floer theory over Z, then something about their frame bordism class. The answer, unfortunately, is no. So this fails. So do I know any examples L and K intersect in 2 points when MXY is fairly explicit? So I don't really know any. So I guess there's a few ways you can get examples. I could take T star Sn, and I could plumb this with another T star Sn at 2 points. So what do I mean by this? I take one T star Sn and another T star Sn, and I connect them at 2 points, kind of like this. And if I let L be this copy of Sn and K be this copy of Sn, then they intersect at exactly 2 points. Though I'm not 100% sure what the gradings of the intersection points are, so that might not help. But here, MXY is going to be empty. Another slightly more interesting example maybe is if I let L be any Sn, I can pick some Morse function on L with 2 critical points. So there's so then I can let K be L sort of pushed off itself by this F. And then there'll be 2 intersection points, which are exactly the 2 critical points. And then MXY is the Morse flows from X to Y, which is probably going to be Sn-1. At least for like the standard Morse function this is. But so remember that we chose some extra data, which was this homotopy in this extra data to the tangent bundles, and that's what induces the stable framing on the moduli spaces. But if you actually change that extra data, you change the framing. So this might not be, as a frame manifold, this might not be Sn-1 with the standard framing. It might not even be 0 in the frame bordism group. And this actually, in some sense, gives you a counterexample to this question here, if you go through all of that. Okay. Does that answer the question? Okay, so yeah, so if L and K have the same Floer theory over the integers, then they don't over the frame bordism ring. And that's sort of, if we wanted to prove the strongest thing that you could possibly prove, which is this this equivalence here, then that would be nice, but we can't. So how do we get some information out of this?
Can I ask a question? Excuse me.
Yeah.
So in this question, so suppose you have L and K that have the same Floer homology, but you're allowed to pick the additional data any way you want.
Yeah.
Do you know then that there is a choice of data so that they do have the same?
Yeah, so that's like, so yeah, that's a good question. I don't know any actual counterexamples. So the reason I say no to this question is like you say, I can take L and K to be the same Lagrangian with different extra data, which is a slightly silly example. But any like real counterexamples, I don't know. That's something
because
I'd really like
in this specific situation that you're looking at, one can expect that maybe with some more assumptions that are global, like maybe the generators of the Fukaya category are finite. Maybe you have a finite family of generators for the Fukaya, which is kind of true in these plumbing examples. Then the expectation is that Floer homology over Z characterizes quite a lot, you know, up to maybe, you know, the Lagrangians. Expectation is that it's hard to imagine things even non-Hamiltonian isotopic with all the Floer homologies the same. But at the same time, it could be that, you know, okay, this choice of additional data can be very different. So I don't know. It was just a question. So
yeah, no, I don't know either. We've thought quite a lot about this actually, and
yeah.
don't have any sort of stronger. We don't have much stronger answers that we can say. But yeah. So yeah, this is the current version of the question that I wrote down is sort of slightly naive for these reasons. But then you could ask the better question, and then we don't know. But yeah, so if we assume that they do have the same Floer theory over Z, we can still recover some stuff without knowing the entire fact that we want, which is that L and K have the same Floer theory over frame bordism. So let's assume L and K have the same Floer theory over Z. And the homology spheres. So in particular, these two together tell us that HF star of LK over the integers is the homology of a sphere. So you can do some sort of basically direct obstruction theory. To try to turn this equivalence over Z to an equivalence over frame bordism. Or I mean, let me change what I wrote, can try to do. To turn an equivalence over Z into an equivalence over frame bordism. Now, if you try to do this, you find an obstruction. Which is some class theta in the n-1 dimensional frame bordism group. So we saw something a little bit like this before. If we know that L and K intersection exactly 2 points, then there's one moduli space that we're interested in dimension n-1, and then theta will actually be that moduli space. But in general, this is just something algebraically constructed. And
a question.
Yeah.
Both for this theta and for the other one, to what extent are they unique, or do you know, or is the construction natural, or
yeah. Construction of theta?
Yeah.
It's, I think, well defined at the sign.
And
so
same for the other theta.
Yeah, for both. So this is a fact that any spectrum with the homology of Sn is of this form. We're using that.
Right, but like it could be of that form for two different thetas.
Yeah, but exactly two different thetas, yeah.
Exactly two. Okay, thanks.
I mean, if you really want it to be canonical, you can probably make it canonical by using choices like the framings we have on the moduli spaces. Yeah, so in this situation, you can probably make it canonical. Yeah, but what we're going to do is it won't matter whether it's theta or minus theta anyway. Yeah. So yeah, if so in the example before, theta is, yeah, this is what I said, but just going to write it. And so this isn't just something that gets in the way of us running the argument. It's actually a complete obstruction, or pretty close to it. So if theta is 0, then L and K actually do have the same Floer theory over frame bordism. And in particular, by this lemma we had before, they have the same frame bordism class, which is what we wanted. But we don't have very much control over theta, is the problem. But what we can observe from here is that the goal that we wanted to study was this difference, the difference between L and K in the frame bordism ring in degree n, and the obstruction was in a different group. It's this class theta in the n-1 dimensional frame bordism group. And these are different groups. So we can try to quotient by this group and see how much we leave alive here, how much of this we don't throw away. So we'll try to, we'll say the strategy is now to kill theta and see what is left in degree n. So what do I mean by this is we're going to take a quotient ring. So I'm going to let R be, and I'll put this in quotes, the frame bordism ring, sort of viewed as a graded ring, modulo the ideal generated by everything in degree n-1. So we kill theta, we kill all of the other things in degree n-1. And the reason I put this in quotes is you actually have to make this construction in spectra, but it's entirely analogous to, or like rather we're thinking of it as a quotient ring. That's how we think of it, at least. But to actually make this construction, you can't just quotient by ideals. Things actually go wrong if you try to do that. But now I can take Floer homology with coefficients in R in this other ring. So LK, KL, etc. over R. And if you want to define this, you could define this to be HF of ... over frame bordism ring, tensor over frame bordism with this new ring R. So all the previous arguments, it turns out, still kind of go through the same. So especially the main technical lemma that I mentioned before, which says things about equivalence over frame bordism implying the same fundamental classes. But now if we try to do the same obstruction theory, we run into the same obstruction, which is this class, I'll call it theta R in the n-1 coefficient group of R. But this is 0, because this whole group is 0, because we just quotiented by it. So we find that L and K actually have the same Floer theory. Over R, this new ring. But now R is a ring that we don't fully understand. So we could ask sort of, what does this tell us about the frame bordism that we originally cared about? So the upshot of all of this is that if I take the difference between L and K in the group Rn is 0. Now this group wasn't a geometrically defined group. We took something geometrically defined and did some algebraic quotient operation to it. But these things being 0 means that their difference in the frame bordism ring lies in the kernel of the quotient map. So the quotient map goes from the frame bordism ring in degree n to Rn. Okay. But this was quotienting by an ideal. So or morally at least, so what we kill, this kernel is the part of the ideal that lives in degree n. So this is, morally at least, is the part of the ideal in degree n. Now remember that the ideal that we had was things generated in degree n-1. And if you kill everything in degree n-1, you have to kill everything which is a multiple of that. And it turns out there's nothing else as well. So this kernel is exactly n-1 degree elements times degree 1 elements, which is the thing that we wanted at the beginning. So one thing that sort of is important is this quotient ring analogy is really an analogy, and it works for the things I've said here, but it really starts to go wrong if I try to look at the kernel of this quotient map in, say, degree 2n would actually be possibly bigger or something. We sort of lose control over it. But that, again, that's fine for us because we only wanted things in degree n. Okay. So I think I'll stop there.
Thank you very much for your talk, Noah. Very interesting. Are there any further questions? So we've had some questions during the talk, but are there?
I have a question.
Sure.
So Noah, could you go back some slides to that lemma that said if you're equivalent in the spectral Foucault category, then you have the same frame bordism class?
Yeah.
Yes. So what's the proof of that lemma?
So I guess firstly there's a precedent for this over Z. So sort of I can tell you how to prove that and then sort of how you change things. So sort of I guess this is a folklore theorem. I've seen it at least once in the literature that people seem to consider well known. But there's a theorem which is not due to us or anything. But if L and K are closed exact Lagrangians and they're like spin and stuff here and graded, if they're quasi-isomorphic over Z, then they have the same homology class in Hn of X. Okay. So how do you prove this? Is I need to use the open close map. So I have a map CFLL, which is C star of L, plus CF of KK. This is chains on K. And the open close map maps this to chains on X. Often you write it as cochains on X, but because these are compact, you actually factor through chains, which is what you wanted. And I send the unit in here, gets sent to the fundamental class of K. Maybe there's a sign here, probably minus. And I send the unit in here to this here. So if I assume these are quasi-isomorphic, why should these be the same? It's the open close map actually gives you a lot more. The open close map actually goes through the cone over the map CFLK tensor CFKL to this, where the map from this to all of this is the product map, where I multiply one way around and then I add this to multiplying the other way around. And if I assume they're quasi-isomorphic, that's exactly equivalent to saying that 1, 1 in this direct sum is in the image of mu2. Right. So if OC goes from this cone, then that class has to die. And this tells you that the difference between L and K is 0. Maybe another way to put it is that there's a null homotopy of the map from here through here and then all the way over to here. And that null homotopy you can still prove using the stuff Tim Large sets up in frame bordism. So maybe a bit more geometrically is the map from CFLL to chains on X. What this counts is I count strips boundary on L and then one marked point over here. And on KK, I count, no, sorry, this is count strips with boundary on L and K, and I count one marked point on the side of K, and I count the same thing with one marked point on the side of L, and I sort of slide this multipoint across.
Thanks.
And so is it a reflection of the fact that that open-closed map goes from Hochschild to something?
Yeah. So you go from Hochschild homology of, let's say, the compact Fourier category to the homology of X, and you actually come from K0 of X maps to this with a trace. So if I start with quasi-isomorphic objects here, then they have to get sent to the same thing over here because they define the same class in K0. Yeah, that's another way to look at this. So that's sort of, this is like a highbrow way of looking at it. But the problem is, if you want to do this in these spectral Fourier categories, they're not yet proved to be an A infinity category. So you can't build Hochschild homology without that. But yeah, that's exactly it.
Thank you.
I have a question. So let's say for T star S8, where you prove that every Lagrangian is diffeomorphic to S8, exact Lagrangian. So can you say something about Lagrangian knot type? So about mutual location of this Lagrangian in the zero section.
Sorry, can you say that again? What do you mean by knot type?
So in principle, I mean, one can conjecture or disprove, right, that all exact Lagrangians and T star S8 are Lagrangian isotopic to the zero section. Okay, and as far as I know, it is unknown. So I mean, the way you're proving that it is diffeomorphic to S8, this unknown exact Lagrangian, yeah, so gives you something, yeah, so to which might or might not capture the mutual location of this Lagrangian and zero section. So question whether you thought about this or...
I mean, I don't know if we can get from this to like an isotopy or anything. Yeah, we haven't thought so hard about that. I mean, it's sort of something that maybe you could do is like upgrading this cobordism to a Lagrangian cobordism or a stable Lagrangian cobordism or something like that. That looks a lot more close to the symplectic geometry, but also looks closer to it looks like a middle ground between the symplectic geometry and the cobordisms. But again, I don't know how to do that. But yeah, that's
this would be nice. Yeah.
So there is I think there is a way to do this, but it's not giving exactly what one hopes for now. So the way would be to first say, if two things are equivalent in the Fourier category, then they are related by an immersed Lagrangian cobordism. And this, I think, is kind of true in the sense that we wrote it in a paper. So hopefully it's true. Let's say, let's put it this way. But Lagrangian cobordism is immersed, so it's not a very nice, object. But now you know that not only they are the same in the Fourier category, but they are the same in the spectral, more refined version. And so you could try to think, could I start to eliminate the self-intersection points of the cobordism? Because maybe I have enough data coming from the spectral part that this could be done. And if you do that, then you'll get actually the true nearby Lagrangian conjecture at the end, in the sense that I think you'll get that not only you have Lagrangian isotopy, but you really have Hamiltonian isotopy at the end. So of course, it's a bit of a dream there, but I think besides a dream, it's kind of maybe a path to think about it.
Yeah, and then another way of constructing these, like if you know you have a generating function, which at least over spheres now we know, and you know that it's defined on a trivial bundle, then you can also interpolate to the trivial generating function, and that also gives you kind of this immersed Lagrangian cobordism. But yeah, I mean, I've thought about it, but I don't know how to then like start eliminating these. And it's not just self-intersection points like the surgery points. I mean, but yeah, it would be amazing, of course.
But but you know, that's what one would need a technique to be able to say, okay, and maybe because you have more data here, it looks more promising than without it. That's what I'm trying to say. I had another maybe comment about this, which is that there is a sort of another way to incorporate the higher dimensional moduli spaces in sort of a Floer type complex, which appeared in some work I did with Barreau maybe around 2003, or I don't know if you know this. It appeared in 2007. But my point about it is that, in fact, you could easily imagine that you mix the two. So our work was using representations of these moduli spaces of Floer trajectories inside loop spaces. Now, your team largest construction, say, represents them in this bordism, frame bordism spectrum. And of course, you could consider the frame bordism of the loop space, which in fact has been done for Morse theory. And this is kind of a ring, so you can take the chains over it. Or so in any case, you could enlarge a tiny bit your theory. I don't know if it brings anything new at the end, but basically the idea is that each right, in all these constructions, the basic idea is that each moduli space has kind of a fundamental cycle, and the fundamental cycle carries some stable framing info, and it carries also, if you send it into the loop space, it's a cycle in the maybe cubical chains over the loop space. And so you can do the smash or some sort of the bordism of the loop space, or these are pointed loop spaces in my story. In any case, you have a bit more info. So I don't know if it helps or if your things adjusts in an automatic way to this case or what, but it looks like you have more data that I think comes basically for free.
Yeah, I'm not sure off the top of my head, but thanks. I'll have to think about it.
I have a question. Maybe I missed this, but where did you use the fact that the Lagrangians were homology spheres?
So if they're quasi-isomorphic and the homology spheres, then I know that HF of LK is that of a sphere. Where did I say that? Here.
I see. So in this obstruction, this theta is only going to make sense for spectra whose homology is that of a sphere. I guess in general, like, this is a pretty special situation, I guess.
So the fact that we assume that the homology spheres comes up when you try to do this obstruction theory and you find this obstruction, which comes from this. Sorry, is that what you mean?
Yeah, I think I understand. So like the higher algebra simplifies quite a bit in this situation.
Yeah. So theta, this obstruction theta is exactly the obstruction to being able to say that the frame bordism HF of LK over frame bordism is the same as the frame bordism groups of SM. So this is actually what you really want, is this statement. And yeah.
Like for other manifolds, the obstructions are just like too complicated.
So you could probably run this for other manifolds. The issue is here that we've used kind of the fact that the homology of a sphere is quite simple, right? You build it from a cell decomposition with 1 0 cell, 1 n cell, right? But by Poincare duality, if I have any more cells, they have to be in degree n over 2, right? Or lower, but best case scenario is n over 2, right? But then if I try to do this same obstruction theory, I'll get maybe a class theta in here, but I'll also get like some other class delta in degrees of where you have other cells. So there'll be something in degree roughly n over 2. You'll have more obstructions. So large parts of this will still work if you keep track of the obstructions and you have maybe a manifold which is not an SN but not too complicated. But the real problem will come up when you try to do this quotient construction. So when you try to quotient by this ideal, this analogy breaks down when you try to quotient by stuff in degree half of the degree that you care about. So you can still make some sort of construction, but then you're going to have to control the kernel, and it becomes more difficult. But does that make sense?
Yeah, to some extent. Yeah. Thanks for the explanation.
So where was it? The fact that we know that these two things equal this is the thing that this equality is what becomes more complicated. And again, you can, if you have some sufficiently simple manifolds, you can probably do some computations and get some understanding of this kernel. But the answer won't be as nice.
So, are there any further questions?